Welcome back. Welcome back. It's time for The Naked Scientist. Dr. Chris Smith joining us via Zoom from the UK, consultant virologist at Addenbrooke's Hospital. Welcome, Chris. Always great to have you.
Oh, hi, Clarence. It's a big week this week, actually. Not just because you and me are back together, because it's been a little while, hasn't it? Because of Easter and so on. But a big South African discovery made 16 years ago yesterday by Lee Berger was Australopithecus sediba. This resonates across South Africa because, of course, it was a huge international story. This early human ancestor, dating back many, many years, but found at Malapa near Johannesburg. Well, Lee's actually in the UK. Phoned me up a couple of days ago. We're going to go out and get some dinner tonight, and he's going to tell me another very exciting story, which you'll have to wait for, coming up on The Naked Scientist, which relates to another very important South African discovery, which will be coming out in a few weeks' time, we hope.
Interesting. So you say that's going to be hard talk for the press, and you're going to share it with us next week.
But we're recognising the anniversary of the amazing discovery of Australopithecus sediba, which I think my daughter was the first person ever to take an impression of that to school for show and tell, because it was, we got the plastinised models of the skull and the hand of sediba because Lee gave me a copy of it. And she was very small at the time. I think she was about 6, 7. Took it off to school, and the teacher said, "Well, what the hell is that you've got in this box?" And it's this skull. And she said, "Oh, that's Australopithecus sediba." And the teacher said, I can't even say that, let alone know what that is. But anyway, they were very impressed to have a model of a caveman from a few million years ago turn up at school.
Okay, let's get to the questions. And I think Artemis, of course, that is the mission that we are watching off to the moon. Goddess of the moon, isn't it, Artemis? And twin sister of Apollo too. So now you get where the name's kind of fitting. But the first question, I'll give you both questions. The mission and the Orion capsule coming back. I want to know, can you tell us more about the heat shield protecting them on re-entry? That's from Eugene in Paarl. And then Anita wants you to please note, it's not Anita, it's Janine wants you to know what caused the millions of perfectly circular, flat-bottomed dents on the surface of the moon.
Hi, both of you. First of all, the return journey. The Orion capsule will be returning to Earth and travelling at a speed of about 25,000 miles an hour. That's pretty quick, even by the speed with which Donald Trump changes his mind. And as a result, when it reaches Earth's outer atmosphere, it's going to run into the atmosphere and create a huge amount of heat. Because in the same way that inside an engine, when a piston comes up in the cylinder in a diesel engine and compresses the air and makes it very, very hot, the compression of the air in front of the Orion capsule will create what's called adiabatic heating effects. And the air will rise in temperature to enormously high levels of temperature. I mean, 1,000 plus degrees, hot enough to melt stuff. And the problem they had before when the capsule came back was that the heating effect was hard to deflect with the heat shield they had. It was causing localized heating, it was causing pitting and burning of some bits of the heat shield, which is an epoxy matrix, which is designed to burn up and effectively turn the kinetic energy of the craft via heat into an erosion effect on that heat shield. So you throw away your heat shield effectively and burn it away to slow down the craft. It's effectively what the brakes on your car are doing when they rub against either the discs or the drums on your car. You're rubbing away brake material slowly by turning the kinetic energy of the car via heat into brake dust. The heat shield will do the same thing. And they'll come in initially at very high speed into the outer wisps of the Earth's atmosphere, which will begin to slow them down quite a lot and produce a lot of heat. This will slow them down quite quickly because you're running into atmosphere, which at that sort of speed and that sort of level of compression is going to be like running into a brick wall. It's going to be quite a slam into the atmosphere as they come in, and it will be bumpy. At the right velocity, they then deploy some parachutes because that stabilizes the trajectory of the craft, but also then begins to capture more air, and then you slow things down and descend into the Pacific Ocean at a much more sedate, gentle pace. and they will make a splashdown, and there's a recovery boat. They'll know roughly what the position is, of course, and so they'll have a recovery boat ready. They'll nip over there, and they will then retrieve the craft. And as one person put it to me, these spacecraft are great for floating around in space. They make terrible boats, so the crew will not be having a pleasant time bobbing about on the ocean until they are retrieved into the back of the recovery boat, which has got a special deck there, an open deck. We can float the boat in, the spaceship, and then get it safely aboard, and then the crew can get out. And of course, everyone's going to be glued to that one. To the moon. This is an interesting question, and we know the moon has an interesting story to tell because it's about 4.57 billion years old, so it's about the same age as the Earth, a little bit younger. The origin of the moon was that a planet roughly the size of Mars, which we give the notional name Theia to, slammed into the early Earth about 4.57 billion years ago. It ejected loads of material from the surface of the Earth up into space around the Earth, and the cores of the two planets merged, and that dust that was ejected around the Earth then coalesced to form the moon. This is the explanation for why our moon is so big compared to the size of the Earth. If you look at most planets that have little diddy moons, like look at Mars, it's got two tiny moons, much smaller than the body itself. Our moon is very big, and the explanation is the one I gave, that there was a giant splat back in history that created it. And the moon actually is credited with having a huge stabilizing effect on the Earth, because being so large and on a stable orbit, it also was able to interrupt a lot of stuff that would have rained into the Earth over historical time. And about 4 billion years ago, 3.9 billion, there was a phase in the evolution of the solar system called the heavy bombardment, the late heavy bombardment. And this is because as all the planets were jockeying for position, the asteroids that were a failed planet out in the asteroid belt were being dislodged by various gravitational resonances and brought into the inner solar system. And many of them crossed the orbit of the inner solar system rocky planets and then slammed into them. So the Earth was getting slammed into on a regular basis, and the moon was as well. And because the moon is tidally locked to the Earth, in other words, the moon, for various reasons, its rotation rate is once per orbit of the Earth, it means it always shows the same face to the Earth. Therefore, the outer side of the moon got most of the smashing into that happened, which is why it has got lots of craters all over it and hasn't been resurfaced by lava, whereas the side facing the Earth has been more recently resurfaced by lava, filling in a lot of the potholes. Wish we had that on the roads in the UK. And that's why you've got two different appearances. But there is a huge great impact crater at one end of the moon, at the bottom end. And that's the one we see in many of the pictures. Absolutely massive great crater, which was a legacy of that bombardment going on billions of years ago.
Let's go to Peloso. It's been a while. Welcome back, Peloso. Go ahead for the Naked Scientist.
Thanks, Clarence. Hi, Dr. Chris. I have a question with regard to cooking pot. There's aluminum. Is there any material in cooking pot that can, over time, cause slow poisoning?
Hi, Peloso.
Yeah.
This question has been asked many times around the world in terms of safety of cooking utensils, because historically we used a lot of iron utensils. Iron, very, very heavy, very expensive, hard to make. Aluminium, very, very light, very easy to work, very readily available now, but originally very expensive to make, but much easier to make now. So as a result, many of the iron cooking pots people were using around the world, and iron cooking, other iron utensils and trays and so on, ended up being replaced by much lighter aluminium. And people began to question, well, is anything able to leach off of these things? When iron dissolves, it makes iron ions. And we need those. They're good for health. We're anemic if we don't have them. And some people even suggested, well, if you look in some communities, people who substituted aluminium cooking pots for their iron cooking pots, there was an increase in rates of anemia, lack of red blood cells, because when people were cooking certain acidic foodstuffs in their iron cooking pots, it was dissolving the iron a bit, liberating some iron ions, which were then absorbed by the people in their food, and as a result, helped to combat anemia. So then people said, well, if that was happening with iron, could the same thing happen with aluminium? And it's certainly true that there are some foodstuffs, very acidic foodstuffs, and the classic one is rhubarb. If you cook rhubarb, it produces extremely acidic juices. This does erode the surface of an aluminium pan. And if you ask a person who works in the catering industry what pans they like washing up the most, they'll say the baking tray that was used to make rhubarb crumble, because it's so easy to clean, because it comes up spotless, because the acid in the food has liberated all of the food off the surface of the aluminium. But that means there is some aluminium getting into the food. Some people say this is potentially a health risk, and there is some evidence connecting aluminium exposure in diet to Alzheimer's disease. Because when we look in the brains of people with Alzheimer's disease and you find the build-up of beta amyloid plaques, which are these protein tangles and deposits in the brains of people with Alzheimer's, in some of those you sometimes see particles of aluminium. Now, what we don't know is, did that aluminium get into the brain and cause that plaque to form, or did the aluminium settle there because the plaque was there, it was already an abnormal site, and it was sticky chemically, and aluminium, being a small, highly charged particle, stuck onto it? We don't know. And so at the moment, the jury is out on whether aluminium can cause this kind of effect or not. So the advice given to people is aluminium cookware is almost certainly very, very safe, very effective, very, very convenient, very, very useful, but probably better not to cook really acidic foodstuffs like rhubarb crumble in your aluminium cookware, just in case.
We have a propensity for cast iron in this country. You may be familiar with our Portuguese pastime. Anything that we should flag there?
Well, cast iron makes brilliant cooking utensils because it holds the heat so well. If you want to make brilliant Yorkshire puddings, cast iron Yorkshire pudding trays are fantastic because the heat retention is amazing. So when you get them out of the oven with the oil in them ready to go and you pour in the Yorkshires and the Yorkshire pudding mixture, then they begin to fry up beautifully in the pots, and you don't end up with them sagging because they haven't got cold before you get them all filled and then back in the oven. So iron is regarded as very, very safe as a cooking utensil, because if you do liberate any iron from the iron, which cast iron is, it's going to help you not become anemic, possibly. And there is really iron in food, and you can demonstrate this. If you get a packet of cereal, get some cornflakes that say fortified with iron, and get the end of the bag, crush up a few of the cornflakes into dust, hold a magnet to the outside of the bag, and then throw the dust out by opening the bag and hold the magnet just there, you'll notice that on the inside of the bag, where the magnet was, there will be iron particles stuck there, and that's the iron which is in the food to help you not become anemic. And your iron cookware is helping you in a similar sort of way.
Okay, let's go to the next question, and it's N from SJ. I'm going on holiday in a few months by sea. Tell me, what is seasickness, please? Besides tablets, how can I avoid it, or any other remedies that you can recommend?
Ooh, well, I hope you have a lovely time, and sorry to hear that you become afflicted by seasickness. We don't really understand the logic of the nervous system behind this. But what appears to happen is that our balance organs, which are the inner ear, the vestibulocochlear system on the inside part of your ears, on each side of your head, this is a system of fluid-filled canals which have hairs projecting into them. When you move, your body bone moves and the fluid is temporarily left behind. That's inertia. And by leaving the fluid behind temporarily, it causes the hairs that project into the fluid to deflect. And the extent, rate, and degree of deflection in any given direction fires off nerve impulses that the brain can use, because these canals are organised in the X, Y, and Z axes relative to your head on each side. The brain uses that to work out what direction your head must be moving in. There is also a system called the static labyrinth, where you have weighted material dangling downwards and acrossways in your inner ear, and this doesn't need movement to send a signal to the brain. It knows basically where you are when you're just standing still. These signals are integrated to work out what you're doing and where you're going at any moment in time. The brain compares that signal with what it's seeing through your eyes, and that computes a balance reflex so that you can keep yourself standing up straight, looking straight ahead, and when you're walking along, keep your eyes fixed on something and on a target. Now, when you're on a boat, you're rocking around all over the place, so this vestibular system is being very heavily stimulated in unpredictable ways because your brain normally knows when you're walking along, it can anticipate the movement that's coming, and it makes appropriate balancing actions to compensate, and because it can anticipate it and can expect it, it's not a surprise. When you're on a boat that's rocking about all over the place, your brain doesn't know where the next movement is coming from. You can get used to the swell a bit, but there's going to be unforeseen effects. And when the brain tries to compare that with what the eyes are saying, the horizon's going up and down and all over the place, this creates a neurological disparity, which in some people, for reasons we don't understand, the brain concludes that the best resolution is to make you throw up. No idea why that is. The remedy? Some people get used to it. Some people find that not being in the cabin of a boat, being up on deck, looking at the horizon, because that is a fixed point that isn't moving, you can keep your eyes firmly fixed on that. This can help. So the fresh air, being outside, firm view of the horizon can help. Getting used to it definitely helps, and it does go away. You do get used to it with time. And there are various anti-sickness drugs. They are usually antihistamines and things like cyclizine and antihistamine, which are non-sedating, but they are very effective at helping some people. So I would go to the chemist and say, what are the best anti-sickness remedies that won't make me feel sleepy? And do a combination of those things. And don't wait until you feel queasy before popping the pills. Pop the pills before you go anywhere near the boat, and you will find that this gives you mental fortitude. Try the other things as well to help you to minimise the risk of beginning to feel queasy, and you will quite quickly get your confidence up that you don't feel queasy, and then you'll be okay.
Douglas, thank you for that question. WhatsApp 072 567 1567, or call 021 446 0567. Di has called us. Di from Constantia, go ahead for the Naked Scientist.
Given my limited knowledge of astrology, I was taking part in a discussion the other day, more from a listening point of view, where there was a simple question: how is it that the current moon exploration is taking place during an 11-year cycle of extreme solar flares? As the reorbiting of the module surely comes back into the Earth's orbit, that solar flare radiates extreme or gives off extreme radiation. Surely this is a consideration, or am I misunderstanding it?
Hello, Di. The answer is that the sun is an active thing and it's not stable. It doesn't do the same thing all the time. It goes through cycles, as you allude to. The sun actually has an 11-year cycle of it reaches a peak and then it diminishes, and it reaches a peak and diminishes. And during this cycle, the magnetic effects on the sun and the activity of the sun, the number of sunspots which reflect that magnetic surface activity of the sun, they change and wax and wane and increase. And we reached a peak in 2024. And so now the sun is beginning to diminish in terms of its activity again on that cycle before it will pick up again. So you're right that when the sun is more active, there's a higher risk of things like ejections, coronal mass ejections and solar flares. And when these happen, we don't understand exactly why they happen, but they appear to be a contortion of magnetic field on the surface of the sun, which then flings material, plasma, charged particles, radiation, at a ferocious rate from the surface of the sun into space. We luckily are quite good at spotting where these are happening, and we are also quite good at anticipating when they're going to happen. So there are actually space weather forecasting programs in operation now, and NASA will have been keeping a very close eye on the sun, on the sorts of things that herald this happening in the run-up to the launch of the Artemis II mission, and also during the mission. There have been activities and bursts during the mission, but they've mainly been things going in the opposite direction because they're quite directional. The sun's huge, and you can think of it as like a lighthouse in the middle of the solar system, shining in all directions, and it will fling these ejections in a certain direction, a bit like the light swinging round on a lighthouse. And if you're in the path of the beam, yes, you're going to get hit by it. But if you're not in the path of the beam, most of it's going to go nowhere near you. And so with that in mind, and the fact that we've not got evidence that there was going to be anything coming our way during the scope of this mission, they were comfortable that the risk, while there's never no risk, the risk was low.
Let's go to Rick's voice note then, Joe.
Good morning. Question for Dr. Chris. The spacecraft that we see and refer to often in the original spacecraft, or right in the beginning, those spacecraft, what propelled them? I'm assuming that it was some form of solar type of energy, other than the fuel to get out of the Earth's orbit. And then if you think about the history of it, I would assume that there weren't necessarily solar power as we know it today. Or can you just elaborate on it a little bit more? Thank you, Ricardo.
Yeah, lovely question. And the Artemis mission had a big array of solar panels because they were going into space for a very long time. It's been a 10-day journey, and you couldn't store enough battery power because batteries are really heavy, so you wouldn't be able to store batteries that would keep your spacecraft running and keep you warm, give you all your effectively life support systems and other telemetry systems and so on for that long. So they needed to generate power. So the European Space Agency made the ESA module, which sat below the Orion module, and that had unfurlable solar panels which powered this mission. The Apollo era, though, did things slightly differently. They actually had fuel cells, so they had ways of generating electricity by pushing their fuel through a generator system that basically reacts hydrogen with oxygen to make water and release electricity in the process. So those fuel cells powered the devices. But the computers in those days used less electricity than a TV remote control, really. They were really inefficient, but they were also very, very small. And as a result, they didn't need the enormous amounts of power. So they took a slightly different strategy with that mission, whereas this mission has been longer, farther, needed more electricity, and they did it with solar power. And solar power in space is great because you don't have the atmosphere in the way. You have unimpeded views of the sun, and you can align your solar panels to get really high performance, and so you can generate enormous amounts of electricity that way, which is what they chose to do.
And we're going to have to wrap it there, but as always, a big thank you to The Naked Scientist. Every Friday after 9:30, you can catch him here. Lawrence, of course, your question came in too late. At 3 minutes to 10 o'clock, we can't get to a very important question. Let's try and get it in earlier next week. Lawrence, please do that. In the meantime, 2 minutes to 10 o'clock then, Natalie Macha standing by with Eyewitness News at the top of the hour.